Okay, so for the last 5 lessons, we're going to go back to video. Seems everybody actually did like them, or for the 3 people that watched them. But anyway, it's going to get a little dicey here because you're going to go into something you've never done before. So we are finally starting to look at why statistics are so important. And you see the title here, Sample Means. Well, what the heck does that mean? First, let's talk about what we've been doing. Up till now, we've been doing descriptive statistics. We've summarized how a data set looks when we look at the measures of central tendency, like the mean, and the measures of dispersion, like standard deviation. So here, we would plot our data and we would say, well, it was mounded, it was symmetrical, it was skewed. Right? Because if it was mounded and symmetrical, then we would do a bell curve and look at a standard deviation. If it was skewed, meaning we had some kind of outlier, then we would do our box and whiskers. So now we want to change from what it looks like to kind of, well, what does it mean? And we try to infer things from these statistics. We try to infer properties about a population from samples that we take. We do this by using probability and sampling variability to estimate how likely a sample is to be in a given population. For example, right now, everybody is voting and sampling the primaries that are going to happen on Tuesday in New York. We couldn't possibly poll everybody. That's what the primaries are supposed to do. So people get a few phone calls. Well, who's going to vote for Hillary? Who's going to vote for Bernie? Who's going to vote for Trump? Who's going to vote for Cruz? Who's going to vote for Mickey Mouse? That's who's getting my vote right about now. All right, so we have a new letter to look at, and it's the population mean, and it is mu, this letter that looks like U. And right now we know the sample mean. So let's just take a second here and look at this. Population mean is mu. Sample mean is x with a bar above it. All right, so we know the difference between a population and a sample. A population is everybody, and a sample is part of that population. It's a subset of that population. So we need to take a little sidestep and set up some background here. So say we are investigating the heights of 16-year-old American males. Now we're going to start here knowing the population mean height. So yes, just for argument's sake here, just so you get to understand this, somebody went and asked every blessed 16-year-old in the United States how tall they were, put it into a calculator, and ba-boom, the population mean height. Standard deviation of 4.2. Hey, that tells us it's a bell curve because we worked with a standard deviation. So now we're going to take the sample size of some 16-year-olds. Let's say we look at the 16-year-olds in Sag Harbor, and let's see how they compare to the population. I don't know about you, but as a coach, it always seemed that every time when I took my field hockey team up island, I crossed the canal, to go play another team, we were tiny. And we'd show up at Miller Place and Shoreham, and they'd have these big girls, and we're like, what's up? How come we're so tiny? So that's how I want to see. We're going to take a sample and compare it to the population. So we are going to sidestep here, and now you're going to have a new program that you're going to see. It's called Norm Sample, and it's on my calculator, not necessarily yours, but you can put it on your calculator. But anyway, hold on. Just watch it. No need for you to really do anything with it. So on my calculator, if I go into program, I've got 3 programs here, all of which we're going to use over the next few days. The first one is sampling of norms. So I'm going to choose number 1, and we're going to run this program. So it's asking me right now, okay, you want me to sample a whole bunch of normals? So what's my mean? Well, we're going to come back up here, and we said the mean was 65.3. See, it's asking for standard deviation because I'm sampling normal, right? Normal means it makes a bell curve. So my standard deviation was 4.2. Now it's asking me sample size. Okay, so I'm telling this about the population. I told the calculator, hey, I got some population here where the population mean, mu here, was 65.3, and the standard deviation of that population was 4.2. All right, so they're like, okay, we've got the basics now. We're going to just randomly select how many sample size? 30. So now it's just going to go out and randomly touch 30 people that would fit in this bell curve somewhere, somehow. And it's just going to randomly select 30 of them. And well, how many times do we want to do that? How many times do we just want to run out to this bell curve that has an average of 65.3 with a standard deviation of 4.2 or whatever it was? How many times do you want me to run into that bell curve and randomly grab 30 people? I want you to do that 100 times. Now, this is a TI-84 high school calculator. It's going to take a while. And no, you're not going to have to sit and watch it. I'll cut out. But here we go. There it is. It's running its simulations. I'm going to go grab some food and I'll be back. All right, so here we are done. It says the sample of the means is in list 1, and the sample of the standard deviations are in list 2. So I'm going to go into stat, go over to 1, and here we go. So 63.45, let me get back to the right page. 63.45 was the lowest average we had. That was the lowest average we had, which was pretty darn close to the population of 65.3. 2 off. Let's see what else we got. What was the highest one we had? The highest one we had was 67.19. Now, it said do at least 200 simulations. I only did 100 for time's sake, but I think you know where I'm going with this. So it is asking for the mean of the means. So what is the average of my means? Well, I can go back here to stat. I can calculate one variable statistics on simply list 1. No frequency, no needed to calculate. And the average is 65.34, 65.3. Wow, look at that. 65.34 is the average of the average. Now, does the title make a little more sense? Sample means we went and we took a sample and we looked at all their means. In fact, we did 100 different samples of 30. The standard deviation of means. Well, let's go look at those standard deviations again. We go into stat, we go back to edit, and we are list 2. The lowest standard deviation was 3. And the highest was 5.7. 3 and 5.7. Once again, we can calculate one variable stats. This time we want to do it on list 2. And look what the average is, 4.2. 4.2! Amazing. Amazing. How does variability of the sample means compare to variability of the population? Is it more or less? Well, we saw that the average height could range more or less, and that the average of the average was very close to the population, and the same, but with the standard deviation, 4.2, spot on. So we stated the sample standard deviation, and it compares to the population standard deviation precisely. So what we're trying to show you is that's how important standard deviation is. It's going to be spot on. When we figure it out, it's explaining the population very well. All right, so the point of this is we're never going to know the population of anything. You just can't ask every single person or survey every single thing. But what we can do is get a large sample and then infer from that sample how the population will react. We have something called confidence when we do that. So let's go back to these 16-year-old boys. We took a sample of 30 16-year-old males and found the mean height to be 66.4 inches. So now we are looking at a sample. This guy, Kirk Weiler, is who we've been doing his lessons all year. He teaches in some school upstate New York. Let's call it Rochester. I don't know where the guy teaches. And he went in his school, grabbed 30 random 16-year-olds, took the average of their height, and he said, since this is a sample, it's X bar, he said their average was 66.4 inches. And now, do you believe this sample came from this population? So do you think that this came from this population right here of 16-year-old American males that we're talking about? Well, let's see. So I went back to the calculator, I went back to where all the data was stored, and in list 1 is the average. And then I went through the average until I found 66.4. Well, 66.4 doesn't exist, but 66.343, that's not it, but 66.413 and above. So that was the 90th term. Remember, I ran 100 samples. So this 66.4 is up in the 90th percentile. So how likely was this sample to come from this population? Not good. It's in the 90th percentile, which means this average is taller than 90% of the average. So there we were able to infer that, hey, these people up here in Rochester, pretty tall compared to the average. All right, so this brings us to what's really happening right now. Like I said, the primary is happening on Tuesday, and people are taking straw polls to see who's going to win. So what we're going to do right now is a straw poll. We are going to give a confidence interval of how confident we are about these straw polls that are going on. So we're going to use a little example here. What we're trying to do is find out how the population, which is never really known, is going to vote based on what we do from a sample. We're going to infer something from the sample of people we talk to. So here it is. We're going to use an orchard. We went out to this orchard and we grabbed 50 ripe oranges. It's a very large orchard, so this is our sample. Took all the 50 oranges, weighed them, and we said the average weight was 212 grams, and the standard deviation was 34 grams. Okay, so does it seem reasonable to use this sample standard deviation as an estimate of the population? Sure, we saw that standard deviation is never really that far off. So now, here's the thing. So there's a bell curve. We got 212, and then we've got 34. as our deviation. So we're going to run this on our calculator. So we're going to run a simulation here. And we're going to look at the 5th percentile sample mean and the 95th percentile sample mean. Now, remember, what the calculator is doing is going into here, and it's taking samples from this bell curve. And then it's going to do its own average to that and everything, blah, 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 and see that when it randomly takes samples from this bell curve, what happens? All right, I'm going to go back into stat. Sorry, we're going to go into program. We're going to take our sample of norm, because we're looking at a normal bell curve, and we said the mean was 212. And we said the standard deviation is 34. Sample size. All right, so I'm going to take the same sample size. I'm going to take a sample size of 50. And I'm going to do 100. And there it goes. Okay, I'll be back in a few. All right, so we're back. So let's see what this simulation got. Going into stat, going into edit, and we've got here as our lowest value, let me see, get my glasses on, we got 201.59. But they wanted me to look at the 5th percentile sample mean. So since I did 100, we're going to go to the 5th one. Come on, calculator, you can do it. 203.7, let's say. 203.7. All right, so our 95th percentile sample mean goes to number 95. I'm going to go backwards, and then that's going to hit to 100. 5 is 219.09. All right, so what does that mean? That means that 5% of the time, we expect the average size of a ripe orange to be less than 203.7. And 5% of the time, we expect the average weight of the orange to be above 219.09. Now, this is very important because as an orange grower, you want to make sure you're sending the same size fruit all the time to who's ever buying your fruit. So now you've got to ask yourself, well, is this true? Is the average size of your orange when ripe going to be 212 grams? You can't shortchange somebody. So maybe you took the oranges from a really sunny section of the orchard. Maybe that wasn't true. Maybe the sample you didn't take was that great. So what we're going to do again is we're going to run this sample one more time, and we want to get a confidence interval. So we're going to try this simulation again, and I'll cut out and I'll just give you the results. And what I'm going to do is I'm going to run it so that I'm going to take this, I lost it already, 203.7. I'm going to take this 203.7 and run it. And what was the other one? 219.09. I'm going to run these as my average size. Well, maybe my oranges are really, really small, or maybe they're bigger than the 212. I don't know. But I'm going to run this again with those numbers. So I'm going to cut out so you don't have to watch it. All right, so I actually ran it with the 203. And I want to see where 212, because that's our average, would lie on a bell curve that had 203 as the mean and the standard deviation of 34. So if I look in here, I've got to find 212. And if I come down here, wow. You can see that 212 is going to be on the high end. 211.89 is 95. 212, well, let's call it at 96th percentile, which we would expect. It's on the high size of this. I'm going to run this sample mean again, and this time I'm going to use 219 as the average. So I'm going to look at the high side as an average and see where that puts me. All right, cutting out again. See you soon. All right, so it's all done. Let's go into our list. Remember, we're looking for 212. So that's going to be below the 219 average we put in. And there it is, right at the 5th percentile. So what did this tell us? Why did we do all this? Well, basically, this is what it told us. That if I were an orange farmer and I tell somebody that my average fruit is 212 grams with a standard deviation of 34, I just gave him a 90% confidence that that's going to happen, that they're going to get a fruit around 212 grams. Because when I took the lowest one and ran samples on it, and the highest one and ran samples on it, the 212 went from the 96th percentile to the 5th percentile. So really, that's a 91% confidence interval because there's only 4% higher and 5% lower. So 9% of the time, we're not going to hit that. So 90% or 91% of the time, we are going to hit it. Well, looky there.